Intel has official Battlemage information for its next GPU architecture. It is 4 a.m. in Taiwan. We've wandered into this park because the story is important enough to film right now. So this is one of the first motherboards with Xe2 on it, which is what's going into Battlemage in discrete GPUs for desktop later. This board was stealthily handed to us at the show with the Lunar Lake integration on a future laptop motherboard. Even though it's mobile silicon, it still features the architecture that'll build the next generation desktop GPUs for Intel. Intel unveiled the basics of its Battlemage architecture. It has a keynote technically going up around the same time as this video, but we're gonna skip all of the AI-infested keynote discussion from the CEOs and instead just focus on the engineering discussion for architecture. Now, on the CPU core architecture side, Intel also has some news. The biggest one is that it is ditching hyperthreading, or SMT. We're going to talk about that later in the video, but we're starting with Xe2 architecture and what we can expect for the upcoming Battlemage. Before that, this video is brought to you by the Fractal Torrent High Airflow Case. The Fractal Torrent is one of the best air cooling performers we've tested, largely thanks to its included 180 by 38mm fans. The Torrent is spacious and easy to work in, with what Fractal emphasizes is a heavy focus on function. The case uses a unique front panel to add some flair without a major impact to performance. You can learn more at the link in the description below. We'll start off with one of Intel's first-party charts. So, Intel showed some charts with clock-normalized uplift against specific functions of the GPU, like a 12.5x relative increase in draw xi, 2.1x normalized increase in pixel blend rate, which comes from some changes we'll cover today as well, a 4.1x increase in mesh shader dispatch, and then some lesser areas of uplift like tessellation. Intel also showed its new Xe2 render slice officially for the first time, and we're finally able to start getting a picture for the changes. Intel's Tom Peterson presented some details to the press, focusing on performance increases from mostly utilization changes and a reduction in wasted processing in the pipelines. This is where Intel is focusing its efforts for Battlemage, and he did the presentation in typical Tom Peterson fashion.
All right, so the XMX is the heart of our AI accelerator, and I'm showing you a little animation. This is showing you 16 by 4 by 4 by 2, which is kind of saying I've got 16 lanes. I can do 4 chunks of 8-bit integer, and I can do 4 at a time because we're 4 deep, and there's 2 operations per MAC. So that's telling you, hey, I've got a lot of goddamn MAC operations, okay?
And we checked, and that is an official unit of measurement. Now, Intel's A750 and A770, we've talked about how they have more silicon than they can really leverage. I think the comment we made previously was that they should be just wrapping the cards in money before they ship them out the door, because they use relatively massive dies at a cost that wouldn't make sense for NVIDIA, for example, to sell that die size, that die area. But the problem Intel has run into is a mixture of driver optimization, and then they also made some architectural choices early on with Alchemist that have limited some of their ability to scale. So that's what Intel's trying to fix. This is a render slice from the original Intel Alchemist architecture. Each render slice is pictured as containing 4 Xe core blocks, and each of those itself contains the vector engines. There's also XMX hardware, load and store, and cache hardware. The render slice also contained 4 ray tracing units, samplers, high-Z, geometry, rasterization hardware, and a pixel backend. This is the new Battlemage render slice. There's some color changes, but you can ignore those, they're not important. One of the larger changes that Intel made is re-architecting the GPU to SIMD16 instead of SIMD8. SIMD means single instruction, multiple data. Moving to native SIMD16 for the engine was promoted as a key change architecturally, and Intel described the change like this, quote, basically, there's 8 lanes of computation for every instruction. We've moved that architecture to be 16 wide, which has a lot of efficiency benefits, but also compatibility benefits. More and more often, you'll see games running right out of the box, end quote. Now, this change also means that Intel's XVE, or Xe vector engine core count, has reduced per Xe core and render slice, but this was an intentional change, of course. The new Xe core for Gen 2 is halved for vector engine count per Xe core. However, Intel tells us that this is countered with the increase in width to SIMD16 from SIMD8. We'll be curious to see if this leads to a reduction in performance anywhere else in the pipeline in rare scenarios, but overall, the biggest improvement should be compatibility. The claimed upside being better day one support for games is really what Intel needs right now for Arc. In our videos, like our most recent Intel Arc 1 year later revisit that we did looking at the drivers, the biggest thing we focused on was that while yes, it has improved, no, we can't recommend it still for people who need day one support for the most recent games because it's not always there. So moving to SIMD 16 natively, Intel says should help with some of this, and that would be a big deal. The next big change Intel highlighted was implementing execute indirect support natively for indirect draw and dispatches rather than what Intel did on the original Xe, which was emulate it. Intel told us that the 12.5x increase in draw XI performance shown in the chart that we saw earlier comes from the native execution indirect implementation. Intel stated this, quote, "This is used by engines like Unreal 5 extensively. Having support for this in hardware is a need for the next generation games." Intel also noted improvements to several other areas. Rapidly, those areas include the geometry block, mesh shading performance, out of order sampling and execution, fetch, high Z, and triangle culling, and also render target prefetch on L2 cache, and even the clear behavior has changed. They've also made improvements to blending and to ray tracing. Intel says that these changes will result in better utilization. Our interpretation of that statement is that it's a waste reduction instead. So now Intel is going to be focusing on, for example, clears. If we take that one, instead of writing zeros to everything, they're marking a bit to say, get rid of all this. We're going to start from scratch on a new frame. And that's just one of the examples where previously, from what Intel was saying, they were wasting resources and burning time on something that could be done in a much more efficient way. And then those resources could be used elsewhere, or just the performance could potentially increase. Changing high Z and culling behavior is also specifically a waste improvement. Culling isn't a new concept. So Intel stated this, quote, "We've redone our high Z. If you think about fixed function, it generally starts with reading geometry, then you're translating geometry using matrix multiply in world space, you're moving these triangles around, eventually you have to get to a point where you show a pixel. You're going to convert a triangle to a fragment, which you're going to shade to draw a pixel. That fragment processing is very important for the order of those triangles in the final scene. High Z remembers which triangle is closest, and if it ever sees a triangle that's further away, it will instantly cull it from the pipeline. It's a trick to reduce pressure on your later shading." So the way they're handling this is a little different, and we'll get into that, but the very basics of culling that basically everyone does at this point would be something like, right now, I am obstructing geometry, if this were 3D space behind me. Maybe it is. We'll find out one day. If I move a little bit, that geometry is now revealed. When I step back in front, it's hidden. There's no point rendering it if I'm blocking it. So typically the way culling works in games and rendering is looking for objects that are obstructing other objects, determining is there any blending that needs to happen, is there a transparency layer, is there some kind of attribute to the foremost object that would affect but still show the rearmost object, and if not, get rid of the rear one. It's not going to be seen anyway. Save that geometry processing for something else. So that part's not new, but more aggressively culling triangles or fragments that won't be seen means, as Tom Peterson said here, later processes can focus resources elsewhere. The improvement should be lower resource utilization on wasted shading to instead allow higher performance or more appropriately spent resources on visible parts of the scene. The pixel backend has also improved. When there are transparencies in a scene, the GPU has to do math to blend the multiple layers of transparencies, and Intel has increased bandwidth for shading to improve performance in this part of the pipeline. The company also stated a 33% increase in pixel color cache, reducing bandwidth demand overall, and that reduction in bandwidth is because more data can be resident in cache, reducing transactions out to memory. Intel also noted these improvements to its geometry pipeline performance. Quote, "On the geometry block, we've improved fetch. We've redone how work is distributed to the geometry pipeline to improve utilization by a ton. Mesh shading performance has improved dramatically with vertex reuse. A lot of times you have a vertex that's used across multiple triangles, and now we avoid a second fetch. We now support what's called a stripe. If you think about DirectX, a lot of the time you have a vertex that's used across multiple triangles. We now take advantage of that in hardware and avoid the second fetch. So this is another waste reduction. Avoiding a fetch keeps that resource for other transactions. Intel also said that out-of-order sampling improvement is necessary to be able to efficiently fetch compressed textures that reside in cache. Intel's approach to sampling is to pull large, sometimes multi-gigabyte textures from cache, and Intel says that it can fetch these more efficiently now. The company also noted programmable offset support, saying, quote, "We're talking about an offset relative to the center of the sample, which allows us to implement higher level filters directly in hardware." So the theme here is there are improvements in hardware. There are some architectural changes, key ones, like changing to SIMD 16 native. But then also Intel is trying to integrate this with the software improvements it's made. So on the driver side, it has been working on fully rolling out its DirectX 11 re-architecting for the driver stack. That's something we covered previously. It already went through DX9, and all of this re-architecting of the way the drivers work means that now, with a more mature driver state, Intel can start combining that with hardware improvements and fixed function changes to, we'll see, become more competitive. Maybe. They probably will have to increase the price at some point, though, because it's too expensive for them to ship those cards right now. But the next big improvement was to the compression algorithm. Intel said it supports a new 8 to N compression algorithm on the Pixel backend. This is when it spoke about clear performance as well, noting that the move to mark a bit instead of write zeros, quote, is a no-brainer, but dramatically improves performance, end quote. On ray tracing, Intel re-explained how bounding volume hierarchies work and then stated that Xe2 is increasing to 3 traversal pipelines, 2 triangle intersections per RT unit, and 18 box intersections per unit. Now, Intel was already actually doing pretty competitively in ray tracing, so in some scenarios it was almost embarrassing AMD, still not up at NVIDIA levels of performance, but it was sitting between the two when it worked well. So if Intel is continuing to work on RT performance and it increases its day one support for games, then it may be AMD that has the most to worry about here. There was a lot more discussion about Xe2 as it relates to specifically Lunar Lake. We'll flash through some of the slides here, but all the stuff we've talked about so far applies to all Xe2 implementations, and that means Battlemage and Lunar Lake both would see these changes. We'll leave out the Lunar Lake specific GPU discussion for today. Processing and condensing all this information abroad is already intensive on the schedule, so let's move on to some of the announced core architecture changes for Lunar Lake, because some of these also apply for Intel's future Arrow Lake solution, which is going to be the next desktop part, and we're hearing rumors that it's probably fall of this year. Intel gave us a deep dive along with other media on its architectural changes for the cores, so P-core and E-cores for Lunar Lake, but this also scales to Arrow Lake in a lot of situations. So these microarchitectural changes, Intel says, are supposed to set them up for better scaling going forward, and their focus was on efficiency and on IPC, but they also, again, talked about dropping hyperthreading and SMT. So Lion Cove P-cores will show up first in Lunar Lake mobile CPUs, and those are the ones that overhaul fundamental design to allow for that scaling going forward. Intel refactored its internal CPU design process and core architecture IP, which it says will continue to give benefits across multiple generations and markets, saying, quote, "Our new development environment allows us to insert knobs into our design to quickly productize the SoC derivatives out of our baseline superset P-core IP. And indeed, the Lion Core version that goes into Lunar Lake is different in several aspects than that which will go into Arrow Lake later this year." So it's not completely shared, but there are some things that we're seeing across both. Getting back to the removal of hyperthreading, Intel says that in general, hyperthreading gains roughly 30% IPC in the same core area footprint in the silicon, which is why it's been used for about 20 years now. It's not free though. Intel says that hyperthreading necessitates duplication of many architectural elements. Filling the pipeline with multiple threads requires hardware to track the execution into the pipeline and the state of those processes. This takes area and it takes power to accomplish. Intel gave some numbers to better understand this. So it created a situation with a hypothetical architecture where hyperthreading is on for one and off for the other, but otherwise everything is controlled. The new efficiency optimized P-cores without hyperthreading would give 15% better performance per watt and 10% performance per area improvement as compared to a P-core built with hyperthreading, but with it turned off. Then, with hyperthreading on, the new optimized core built without hyperthreading still wins by, they say, 5% in performance per watt, but falls behind by 15% in performance per area. That loss is where the new E-cores would come in, which we'll get to shortly, and platforms that purely consist of P-cores would still benefit from hyperthreading in this situation. Now, buzzword warning here for AI. So Intel has updated thermal and power controls. Thermally, they stated that the predetermined static guidelines are gone, and instead Intel is moving towards quote AI self-tuning controllers, which would actively monitor and adapt to the specific workloads that are being run. Intel is also adding finer grain clock control at 16.67 megahertz clock intervals. Intel gave the example of a workload where the max theoretical clock was 3.08 gigahertz. Intel's previous 100 megahertz steps would have the core cap out at 3.0 gigahertz. But the new 16.67 megahertz steps would allow for a 2% higher clock of 3.067 gigahertz. On the flip side, this also gives better control in power-constrained situations, like a laptop. The end result should be higher sustained clock speeds for given power budgets and thermal constraints anywhere on the curve. Other improvements include a much larger instruction prediction block, larger operation cache, and deeper operation queuing. Vector and integer operations, Intel says, are now in separate pipelines with separate schedulers for out-of-order execution. Updates to the memory subsystem were detailed by Intel as including reduction in latency of the nearest L0 cache and adding an intermediate L1 cache to create a 3-level hierarchy. Total per core cache capacity is slightly up overall. Some really quick notes here as well. So Intel threw a couple numbers out there. For one, they claim an average of 14% more performance at the same frequency for one P-core in Lunar Lake versus Meteor Lake. And remember, some of this will scale to Air Lake, but not all of it will. Ultimately, mobile is a different thing. Performance per watt ranges between 18% more at the low end of the power range and 10% more at the higher end versus Meteor Lake. And once these updated P-cores make their way to the desktop platform, we'll obviously thoroughly benchmark them and look at how they perform in Air Lake. But for now, some quick notes on E-cores as well. So these are called Skymont. Are we back to... Please don't bring us back to Skylake, Intel. We got away from it. Skymont. This one is the biggest change from the previous generation, and it's upping the core count from 2 to 4 cores per cluster with the removal of hyperthreading on the P-cores. Intel is betting that its new E-cores are good enough to pick up the slack on multi-threaded workload. Quote, our E-cores are getting so good that we can deliver better than SMT or better than hyperthreading performance without hyperthreading. That's the key motivation for making the P-core wider and extracting more performance out of every megahertz. The updates to the individual cores themselves are similar to the changes in P-cores. Instruction caches are larger, queues are deeper. The core is much wider in general, with vector capability being roughly doubled. Intel says vector is generally the type of compute that AI leverages as well, so it wanted to focus on that. The E-core memory subsystem was also updated. And there's also more cache available overall, with 4 megabytes of shared L2 between each 4-core cluster, with double the bandwidth compared to the previous generation. For performance, Intel gave some single-threaded performance numbers between the low-power islands of the previous generation Meteor Lake and Lunar Lake mobile CPUs. Integer functions were up by an average of 38%, and floating-point vectors up by 68% claimed on average, though Intel's graph has one outlier. Overall, in a single-threaded scenario, Intel says the new E-core uses 1/3 the power at the same performance. It says 1.7x more performance at the same power, and 2 times the performance at the top end with the new core using more power. Moving to multi-thread, Intel says total performance uplift on the low power island is heavily increased due to 2 things. The cores are faster, and the increase from 2 to 4 E-cores per cluster also contributes. Integer performance is again 1/3 the power at the same performance, 2.9x more performance at the same power, 4x more performance at the top end, using much more power. And Intel gave an interesting performance comparison for desktop where it put the new Skymont E-core against the outgoing Raptor Cove P-core. This is inherently an uneven comparison since P-cores scale higher with higher power and frequency, but the bottom half of the curve is interesting. There are a number of other improvements as well, like bottom-up scheduling, thread director changes, but we'll talk more about this once desktop starts shipping. So that's going to be all we have for you on this for now. It's a huge amount of work to not only read and study and write this type of content remotely, but also do all of the editing for it. So we put together as in-depth a detailing as we can using Intel's Architecture Day information. They had a ton more information out there. There's probably another 4 or 5 hours of content that we need to work our way through and see what we want to detail for you all in future architecture pieces. But for now, that gets us started. And for us, at least, the Xe2 future desktop Battlemage implementation is going to be the most interesting out of all of this, and it sounds like the biggest changes are going to be possibly to early support for games alongside the improvements overall in reducing wasted processing time, or as they call it, utilization improvements. So that's it for this one. Thanks for watching. As always, subscribe for more. We're going to skip the keynote. Maybe we'll come back and cover it in news or something if it's interesting enough. But I've had enough AI buzzwords this week. I think between NVIDIA and AMD, we had around or over 200 instances of the letters AI. So just skip the Intel one for now. You've got the information that really matters, though, for the core audience here. Thanks for watching. Subscribe for more. You can support us directly by going to store.cameras.nexus.net and grabbing a shirt like this one, or just go watch some of our other videos from our Computex coverage, because we have a lot online already, including a ton of cases and coolers. We'll see you all next time.